Ma'am, you are on mute.
All right, is it okay now?
Yes, ma'am.
Yes, all right. So let us go to today's lecture. So we are going to continue looking at myosins, and just a quick recap of what we had studied about myosins in the last class, last introductory class for myosins. And what we had seen is that unlike actin and tubulin, actin is a single polymeric chain, or a single unit of actin monomer, which polymerizes to give you the actin filament. Tubulin is a dimer of alpha and beta tubulin, and that polymerizes head to tail to give you the protofilaments. Protofilaments attach as shades or can even polymerize as the cylinder grows. We're not quite sure which of this mechanism works, but maybe both work. So it's still something that people are looking into. And then we looked at myosin structure, and myosin structure was different. Why? Because myosin structure didn't have one or two polypeptide chains, but had six polypeptide chains, right? And the six polypeptide chains included two heavy chain and four light chains. So if you take if you're able to extract myosin, purify myosin, and you run it on an SDS page, you will end up seeing at least three bands. So the heavier band would be for the heavy chain, and the lighter bands would be for the light chain. How light? About say 19-20 kilodalton. How heavy? Above 200 kilodalton. So that's a huge size difference. And when we look at the heavy chain, we see that the heavy chain has a globular head and has a helical tail, and between the globular head and the helical tail, there is a region that is flexible, which we would call the neck region. And along this neck region is bound the essential light chain and the regulatory light chain. So two small polypeptides are bound to the neck region of these myosins. And two such heavy chains intertwine together to give you one myosin unit. Therefore, this is an essentially the repeat unit, if you call, in a sort of oligomerized or polymerized myosin filament. So this is the repeat unit. It will have two heavy chains and two essential light chain, two regulatory light chain. Now, as the name suggests, essential light chain is something that is very much required to maintain the conformation of the head with respect to the tail and everything. So it's essential for this structure to come together. Whereas regulatory light chain would have something to do with the regulation of the activity of myosin, right? Um, okay. So what we had also seen is that there are some activities uh, that are denoted to certain regions of myosin. For example, if you look at this helical tail, that the helical tail is the region that is responsible for forming of oligomers or forming of multimers of myosin. So the two myosin tails can intertwine further and give rise to this myosin polymer. And the head region is the region that has two distinct activities. One is the actin binding activity and one is the ATPase activity. So myosin can bind ATP and hydrolyze ATP and can also bind actin. And these two activities were found to be in the head region, but in opposite parts of the head region. So if you imagine like a globe, then imagine two opposite regions of that globe. So ATPase activity would be on one end, and you would have actin binding activity on the other end. We had seen this classical paper where they were looking at myosin heads, and they found that if you just have myosin heads, it's enough to induce ATPase activity. So it can bind and hydrolyze ATP. It does not need actin for this. So even in the absence of actin, myosin is able to hydrolyze ATP. But what does seem to happen here is that although it can hydrolyze ATP, it's very rapid hydrolysis of ATP, that kind of plateaus. Whereas if you add actin, this plateau is not reached and it just keeps giving you more ATPase activity. So this curve kind of keeps increasing, which supports the idea that ATP, that binding to ATP and hydrolysis of ATP is an inherent property of the myosin head. It does not quite require actin for this. But maybe the other activities of myosin, such as the movement of actin filaments, that the force generated on actin filaments, is dependent on ATP hydrolysis. So what is the fundamental scheme that we are looking at? The fundamental scheme that we are looking at is as follows. So you have a myosin head which has an ATP binding site and an actin binding site. So as long as it is bound to ATP, this head does not have the ability to bind to actin. It binds to actin only when the ATP is hydrolyzed to ADP and PI. Now this structure, so again, let's recap what we had done for actin or we had done for even tubulin. We had said that there would be three distinct states, right? There is one state, one conformation when it is bound to ATP, one conformation when when ATP has been hydrolyzed, but the inorganic phosphate is still present in that groove. So ADP plus PI. Another state when the inorganic phosphate is released and it is bound just by ADP, right? Let's put that notion here. So you have the myosin head, which has bound to ATP, and this head is not able to bind to actin. But this head has an inherent ATPase activity, so ATP is spontaneously hydrolyzed. You can see this here. You add ATP to simple myosin heads, you will see a spontaneous ATP hydrolysis. So that would occur. You would have ATP plus PI. This has a low affinity for actin. So it seeks out actin binding sites and it binds to actin with low affinity. Now, in this position, when the inorganic phosphate is released, there is a change in orientation of the myosin head with respect to the tail and the neck. So this change in orientation of about 45 degrees. So it's change in orientation here. That creates the power stroke. That creates the power stroke, as you can see here. And then this pivoting of the head, the release of inorganic phosphate, and followed by the sliding motion. Every time it cocks, it kind of slides the actin, and now the actin has actually moved, right? So it's like this, it binds and it moves, it binds and it moves. So there are distinct steps in this. And when it moves the actin, when the filament slides, at this point, the ADP gets released and ATP binds to this myosin head. And when it is bound by ATP, we know that it does not bind to actin, so it is released from the filament. So this process keeps going on. All right, so this is what we had seen in the last class, and we are going to come to a very classical experiment that we are going to refer to time and time again in our lecture, which is the use of something called an optical trap, optical tweezer, whatever you would like to call it. So this whole idea of optical trapping and optical tweezers is credited to Arthur Ashkin. And Arthur Ashkin is a physicist who worked for a considerably long time in Bell Laboratories, and he started with working with the properties of an atom's nucleus. You have to imagine the time of 1947 when he was starting his research career, and then he moved on to try and understand the effects of light as such. So here was Arthur Ashkin, you can see him here, and he was kind of studying how sort of matter behaves in the presence of laser. So at that time, the whole field of laser was kind of in its infancy, and people were trying out multiple things with laser. And Arthur Ashkin went into the field with trying to understand how matter behaves in the presence of laser. And that gave him the whole idea of working with optical or developing optical tweezer as as a method to study matter. And he also obtained a Nobel Prize in Physics in 2018 for his contributions towards development of optical tweezers. So Arthur Ashkin, he didn't quite call them optical tweezers. He was calling them this single beam gradient force radiation pressure particle trap. Big name, and we will come to each of these to understand exactly, like in very nutshell, what exactly this means. So single beam. So you have a beam of radiation, a single beam of radiation, single beam of laser. All right. Radiant force. What would that be? So in if you look at the way the if you are able to uh, put incident light on a lens, and the lens is acting to converge the parallel rays of light. What happens is that you are at these points you are creating a gradient of light, and the gradient can be visualized as a sort of a Gaussian distribution of light intensity. So if you look at this, if you look at the way the do I have another image of this? Mhm. And okay, so if you look at the way the lasers are lensed through an objective lens, you would see that there are regions near the focal plane where you would have very high intensity of the light, and away from that you would have lower intensity of light. So you actually have created a gradient of of light. And then comes the idea of this radiation pressure. So there are a few aspects to it. Let's look at it one by one. So you have this lens, and you are illuminating the lens with a laser beam, with a laser beam, and the lens is going to focus the laser beam, right? And this, as I said, is going to create a Gaussian intensity profile. So you would have very high intensity of light here, you would have low intensity of light at the sides. So but the intensity of and this and so now, what Arthur Ashkin found was that when he put some particles under this laser, those particles seemed to always move towards the center. They seemed to somehow align themselves towards the center of this laser beam. And what kind of particles was he using? He was using kind of polystyrene beads. He was using, he even used bacteria, cells. So they all seem to come and align towards the center of this beam. Now, what are the kind of forces that are acting on these particles that help them to align themselves towards the center of this beam? So if we think about that, we would come across two events. One is that when light hits matter, then because there is a change of refractive index between the medium through which light is propagating and the medium on which it hits, which is this particle, let's say a bead, then there would be cases of reflection, refraction, there would be scattering. So if we now imagine the light to be made up of, so light has energy, right? So if you think of energy, if you think of E equals to mc square, you could even put E is equal to momentum into the velocity of light. Instead of mc square, you could write it in terms of momentum and velocity. So this momentum, when the light hits these beads, then the momentum is kind of transferred to these beads, right? Because there is collision. So there would be a change in momentum of these beads. That's the first thing that hits it. The second thing is that these beads and these materials would have a dielectric, which means that you imagine this to be some sort of, it's a very small analogy, but let's think of it this way. Suppose you have a flag, right? 26 जनवरी गई तो हमने flag hoisting देखा है. So suppose you think of a flag and you think of wind, and now it's more like a flag that gets caught with the wind. So that's exactly what's happening here. You have a dielectric and you have an electromagnetic radiation here. And the dielectric gets caught in the electromagnetic radiation. So two effects coming into force. One is the momentum that is change in momentum that is obtained because the light hits these beads. And the second thing is that the dielectric bead is getting caught in the electromagnetic radiation that it is facing around it. So both of these properties come together to focus or to push this bead back into focus. So you have one property here, which is the scattering of light, which is transferring momentum and which is sort of making it move away from the field. But you also have this the electromagnetic radiation that is pushing it back into focus. So two of these properties of the way the light is interacting with this matter is helping to keep this bead in the center of this Gaussian profile of this radiation. And here, this is actually an image taken from Arthur Ashkin's own paper, where he's explaining exactly how this is happening. This is a lens here, and you can see a bead here. You would see the light falling on this. You would have some amount of scattering, reflection, refraction, everything happening. And then this is the sort of an actual image of the way the light is moving into this plane where you would have this bead, and then how the light is sort of moving out of it. So you could see exactly how he is envisioning the whole event to occur. Okay, so this is kind of in just in a nutshell what Arthur Ashkin's whole idea of a gradient force radiation pressure particle trap is. Obviously, it has a lot of physics, and I'm not delving into it. Part of the reason being that I'm not a physicist, so I don't really understand the whole nitty-gritties of it. But I'm just trying to give you in a nutshell what exactly the physics aspect of it is. It's all about how the light is going to interact with the matter. There would be refraction, reflection, and there would be scattering of light, and all of this is going to create a change in momentum for this particle. Also, you have if you think of this matter as having a dielectric, that the dielectric is getting caught in the electromagnetic radiation. Therefore, all of this combined together is going to keep or create a condition where this particle, even if you push it out of at the edge of the beam, you would see that it gets pulled into the center. So even if you somehow manage to push it at the side of the beam, it goes to the center. Alternatively, if you have the bead in the center of this laser beam and you push your laser beam around, you would see that the particle tries to move back to the center. Okay, great. So this was something great, but why are we talking about optical trap, or how is that relevant to us? See, the whole idea comes from this. You need when you're working with cells, and you would like to look, or you'd like to stretch the cells, pull the cells, or just about tissue. Maybe tissue is a better example. You're looking at a muscle, and conventionally, if you would like to see a muscle contract, relax, and how much can it stretch. Then you can hold the muscle fiber with tweezers, with things that can hold it at the side, and then you can simply pull it and see how much of strength or how much of force it can withstand, right? And when would it break? How much can you stretch it? How much can the displacement be? And at what point would it break? So that is something that you can do by holding at the two ends. Now think of this holding in terms of not a muscle fiber, but in terms of, say, a single actin strand or a single myosin, a single microtubule. So how are you supposed to hold these filaments? Because these are tiny filaments, right, of the order of nanometers. So how do you then hold these filaments? That's the question. So that is where optical tweezers come in, and that's the reason they're termed tweezers, because it gives you an ability to hold something. Now think of it this way: if you have two beads attached to the ends of a filament, somehow you're able to attach a bead to the end of an actin filament, to the two ends of an actin filament, and you're able to have two laser beams falling side by side, so that when you have the two beads trapped in that optical on that laser line, you can actually hold this entire actin filament between these two beads, much like the way you were holding the myosin fiber. Much like the way you're holding the muscle fiber. So that's the reason we are so interested in optical tweezers, because it gives us a way to hold things. And not just it gives us a way to hold things, it also gives us a way to measure things. So we will come to that. Okay, so optical tweezers use light to manipulate microscopic objects as small as atoms. So this we have understood. So we have already seen that it would require the use of a laser beam. So radiation pressure from a focused laser beam is able to trap small particles, and we have seen how. We have at least tried to understand that this laser beam, when focused, would have a Gaussian intensity profile. That is, at the center of the laser spot, you would have the maximum intensity of light, and as you go towards the side, you would see that the intensity profile decreases exponentially. So maximum intensity at the center, and as you go towards the side, you have lower intensity. So this sort of creates a gradient of of intensity, light intensity profiles. And we have seen the sum of forces from the laser bead system can be split into two components. One is the scattering force, pointing in the direction of the incident light. So one that I said is that when light hits these beads, you would have some amount of scattering, right? If you have the bead in suspended in water, which is mostly the case because we are dealing with biological systems that work in water, in an aqueous medium. So then you would have mean scattering, where you would see that when you have incident light falling on this bead, you will have scattering, and the scattering can be thought of as coming back in the same direction as the incident light. So that's one thing. And the gradient, so this is one component, and the gradient force arising from the gradient of Gaussian intensity profile and pointing in the XY plane towards the center of the beam. So what is it? So again, you have this bead, you have light falling on it, right? And you have the light falling on it with the center of this laser spot having the maximum intensity, periphery having lower intensity. So on this XY plane, you have a gradient of intensity profile, a Gaussian gradient of intensity profile. At the same time, you have light falling on this bead, and there is scattering occurring, which happens in the same direction, or the scattering is occurring in the same direction as the incident beam. Both of these two systems is helping to keep this bead in the spot, suspended in the spot. So you're able to hold the bead in the spot. So if some external object like a molecular motor were to pull the bead away from the trap, a restoring force would be imparted to the bead and thus to the motor. So what is it? Let's forget the motor. Suppose you have this bead which is now trapped in this optical trap, and by some means you're able to push this bead out. By some means, let's not think what means, but by some means, if I'm able to push this bead out, then what will happen? There would be a imbalance of forces on this bead, right? Because now you have changed the gradation, the intensity profile, the Gaussian intensity profile that was falling on this bead. So you've changed the way those forces were acting, the electromagnetic forces were acting on this bead. You've changed the way the scattering forces are now going to be acting on this bead. And everything together would try to restore the position of this bead back to the center of this laser spot. So that's exactly what you see when you are shining, when you see an object like a bead under an optical trap. You would see that as soon as you bring the optical trap near the bead sort of moves into the center. And now if you slightly move this optical trap, you would see that the bead too follows the optical trap. It kind of tries to get position itself in the center. So there is a restoring force that is acting on the bead. Okay, so how much of force or what kind of force is that are we talking about? What is the value of this force that we are talking about that is acting on this bead? So the value comes in the range of piconewtons, and as we have seen repeatedly, uh, the 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 forces that act on a membrane when actin is polymerizing is of the order of piconewtons. The force acting on a membrane when tubulin is polymerizing is also of the order of piconewtons. And we will see that the force that is generated by myosins is also of the order of piconewtons. So this is a good method to actually study these motor molecules because you are able to go to the range of piconewtons. Now, let's get back to something and some other basic physics here, and that is to do with Hooke's law, classic Hooke's law. So, what was Hooke's law? Anybody remembers Hooke's law? I've already put that slide though, but anybody remembers Hooke's law? Sarika? Sorry, Sarika? You
Yes,
remember
ma'am.
yes, Hooke's law?
It's like an equal and opposite force.
हाँ बहुत सिंप्लीफाई करके अगर हम बोलते हैं तो हाँ इक्वल एंड ऑपोजिट फोर्स तो है ही सो बट नॉट how do I say it? It's not the point is not equal and opposite force. The point is this. So here you see in this image there is what do I show here? Or anybody else would go like to go with Hooke's law?
In a certain distance, force and displacement are in proportionality.
Right, right. Which means that you can scale the force in terms of the displacement, not in terms of displacement square, cube, or some power of displacement, but the power of displacement here is 1, which is very important for to analyze these optical trap measurements because okay, let's look at this. So what did Hooke do? What Hooke did was he thought of a spring that is attached to a wall, say a wall, a rigid boundary, and you have a ball at the end of the spring. Now if you displace the spring by say a certain distance x, then you would need a certain force. If you're moving this by a distance, say 2x, then how much of force would you require? You require twice the force, you require 3 times the force, or what's the amount of force that is required? So he did this and he found that the amount of force that was required was 2 times, which means that the force acting on this spring is directly proportional to this displacement. And so we write it, we write this whole thing as force is equal to minus kx, where k is a constant. So it depends directly on the displacement. So now here in optical trap, you are talking about the displacement of a bead, right? And you're saying that there are some restoring forces which brings the bead back into the position. Suppose you provided enough force that it is made to stay away from this laser trap. Suppose. So then the amount of force would be directly proportional to the displacement or the distance that this bead has traveled. Why? Because of Hooke's law. So you can directly estimate the amount of force that is acting on this bead by estimating the displacement that is occurring on this bead. So if you can understand कितना displace हुआ है, you can understand कितना force लगा है ये करने में. So that's the whole idea. So Ashkin, he did all the physics, right? Remember this person here, he has done all the physics to understand. He has, first of all, he has shown that this can occur. That if you put these beads under the laser beam, not just beads, even if you put cells, bacterial cells, you can trap them. It's almost like holding them in place. And then he did the physics to understand why exactly this is occurring. What kind of forces are acting on that particle to keep that particle trapped? And what are the kind of particles that you can trap? You can trap atoms, you can trap beads, you can trap biological matter such as microorganisms, bacteria, etc. So you could range of things. Now in comes a person who was studying motors, biological motors, and he decided that we should be using something to actually measure, quantitatively measure what kind of forces are acting on these biological motors, or what kind of forces are exerted by these biological motors. So James Pudick, he sort of went ahead and used these optical tweezers to understand the properties of these motors. So here is a small setup of optical trap or optical tweezer. And essentially what you require for an optical trap or an optical tweezer, anybody who has done a course on this, any idea? Is any of you doing a course in biophysics kind of thing from Saurabh Raj, Professor Saurabh Raj?
Yes, ma'am, I did last semester.
Okay, can you go ahead and explain what is it that you require in an optical tweezer? Simple,
A
basic
laser,
component.
a laser beam,
Mm-hmm. And okay, so a laser beam is for sure, but you need something to focus the laser beam. So you would need to bring in lenses, right? You would need to bring in lenses, multiple lenses. Then you would need something to be able to sort of visualize the bead, because आपको bead देखना है ना? So you need a microscope. You need a way to be looking at that bead. You need a microscope to see the bead. क्योंकि bead आपको दिखेगा, आपको actin दिखे ना दिखे, आपको myosin दिखे ना दिखे, tubulin दिखे ना दिखे, दिख भी सकता है अगर आप फ्लोरेसेंटली टैग कर लेते हैं तो वो भी दिख सकता है, लेकिन आपको एटलीस्ट बीड देखना पड़ेगा कि बीड का पोजीशन कहाँ है, उतना तो आपको देखना है. तो यू नीड अ माइक्रोस्कोप, right? So you need a system of lenses that is able to then focus this intense laser beam. You need a microscope to be able to visualize those beads, and you need other accessories, other things, but I'm not going to into the whole setup. What I'm trying to say is that this here is, and you need a detector, because agar आपको देखना है कि कहाँ तक ये बीड मूव किया है, तो उसको डिटेक्ट करने के लिए भी आपको किसी तरह का डिटेक्टर चाहिए. सो यू नीड समथिंग दैट इज गोइंग टू होल्ड द बीड इन प्लेस. फॉर दैट यू नीड अ सिस्टम ऑफ laser and pencils, and then you need to be able to see the bead. You need a microscope for that, and then in the end you need a detection system so that you're able to see exactly how much of movement has occurred. Because see, the entire idea of working with this is finally to see कितना displacement हुआ है. Displacement से आप सारा कुछ निकाल सकते हैं. जैसे यहाँ पे मैंने दिखाया, you know the distance it has traversed, you'll be able to get to the force. Okay, so this is how it looks, very messed up. Essentially, बड़ा सा optical bench है. You would see multiple lenses kept there. You would see laser lines. You would see a microscope. And you would see some kind of a detector system. Okay. So what did James Purig do exactly? So what James Purig was not using one laser beam, but using a dual beam. He called it the dual beam optical trap. So dual beam optical trap में, so as the name goes and suggests, you do not have one optical, you do not have one single laser line that is holding one bead, but instead you will have two laser lines which would be holding two beads, which is good for us because if I would like to have an actin strand which is bound by two beads and this is held somewhere in space, and is not moving much, then I would like to hold the two beads essentially. तो दो beads hold करने के लिए मुझे दो beams चाहिए, तो दो beam यहाँ डाल दिया है. This is how the two beams are. You can see that the bead is always trying to get into the center of this laser spot because of, as I explained, Gaussian profile of laser intensity plus scattering. All of these forces play in a way that helps this bead to come back to this position. Perfect. So the first line is that they have this actin attached to the ends of the two beads. What's the second thing that he did? The second thing that he did was he took another bead now and he put a myosin attached to it. And by now we have understood that just the part which is called the heavy meromyosin. Heavy meromyosin, do you remember what was heavy meromyosin?
The portion with
What?
the head.
Yes?
Portion with the head.
Portion of the head. So portion of the head, a little bit of the neck was also there, right? So if you digest this with trypsin, you end up with the heavy meromyosin. You digest myosins with trypsin, you have the helical tailpiece apart, a little bit of the tailpiece, portion of the neck is there, and the head. So essentially all the mechanisms that can bind ATP, hydrolyze ATP, and then bind actin, all of that is present in heavy meromyosin. You need not use the entire myosin. So thank you, Gavan. So what he did was he used heavy meromyosin and he attached the heavy meromyosin to these beads. And so if the heavy meromyosin, the whole idea is that if the heavy meromyosin is attaching to this actin and is creating a pull on the actin, so if it is moving the actin, then consequently you would see a motion of the bead. So if you see a motion of the bead and you know how much it has moved, you will know how much force this myosin is generating on that bead. So very simple idea, but not so simple to execute. Essentially, you have to create this whole system. It's not so simple, but multiple labs have done it, and now optical trap is something that is very heavily used in research. But that at the time when Sputnik did this, it was kind of a revolutionary way to see myosins, and not just myosins, these molecular motors. Okay, so let's look at a little bit on this experimental setup. So you have a firm attachment of silica beads to a microscope cover slip. So you have a cover slip and you have these beads attached to the cover slip. These beads, I'm not talking about these, but these beads. And what you can think of now is that you are trying to coat these beads with heavy meromyosin. And your idea is to look at, see I'm going to give you what the problems are going to be here. So your idea is to measure the force that is generated by one heavy meromyosin. But when you're attaching a bead to heavy meromyosin, and then when you bring the actin filament close to it, there is no guarantee that there would be just one heavy meromyosin on that bead, because आप जब attach कर रहे हैं आप you are not able to control this the number of heavy meromyosins that will be attached to the bead. There could be 5, there could be 10, there could be 15, right? So because you're not able to exactly put one heavy meromyosin on one bead, so the idea is to coat low amount of heavy meromycin per bead. So bring down the number of heavy meromycins per bead. So you bring down the amount of heavy meromycin that you are trying to attach to the bead. If you have too many, then chances are that too many heavy meromycins will be attached to one filament. And instead of looking at the forces generated by one heavy meromycin, you'll be looking at forces generated by multiple heavy meromycins. That's not your idea. So low numbers have to be added there. So then you have this caught in the middle. Okay, ye to ho gaya. Let me see if there is something sparsely coated. Okay, now how do you then measure the force generated? As I said, the force generated is measured by the distance that, or the displacement of the bead. So if you're going to somehow be able to record the image of the bead, so your image, so basically माइक्रोस्कोपी में जैसे होता है, आप आंखों से देखते हैं या फिर आप किसी एक फोटो डायोड के ऊपर लाइट इंटेंसिटी का जो भी प्रोफाइल है उसको डालते हैं एंड देन यू सी एन इमेज, राइट? सो आप उसी तरह अगर आप इसका इमेज जैसा लेते हैं एंड you take that with a with a photodiode detector for high resolution position detection. Essentially, you take like an image and you know that, okay, now it has moved from this position to this position. So you're able to record the positions. So इतना तक आपको समझ में आ गया कि ये सेटअप क्या है. सेटअप है कि हमने दो बीड यहाँ बीम्स में लेजर बीम्स से हमने दो बीड को यहाँ पे फिक्स कर दिया है in mid solution. So this is in solution and you have these two beads in solution. You have ensured that you are picking up the actin with two beads attached to it. So here is another thing. When you're attaching beads to actin, you could have one bead attached to the end of actin. You could have two beads attached to the two ends of actin. So when they were trying to trap, they had to trap those actin which had two beads attached to its end. So that was done. Then they had a cover slip या फिर एक स्लाइड जिसके ऊपर बीड्स है और उस बीड के ऊपर से हमने मायोसिन्स अटैच किया हुआ है एंड लो नंबर्स ऑफ मायोसिन्स सो दैट there are low chances that you would have two or multiple myosins acting on the same actin filament. So with this system, they went ahead and then the idea is to slowly change the focus of this laser beam so that you lower this actin onto this onto the surface of this myosin so that the myosin can now start to interact with it. So this is these are the images directly from Spudik's paper. And what does it show? It shows you two things. So one is that जब हम ये beads देखते हैं, the beads are not going to be very stiff and stationary. Why? Because there is always Brownian motion. So थोड़ा बहुत ऐसे वो हिलता रहता है. तो आपको ये दिखेगा यहाँ पे आपको वो थोड़ा बहुत हिलता हुआ दिखेगा. But every now and then you see a rise. Every now and then you see a distance. So what's happening is this. Think of it this way. So the bead is there. The bead has faces Brownian motion, right? So it's a little vibrating here there, but it's kept in position क्योंकि इसके ऊपर वो laser profile है पूरा जो भी balancing forces है, it's keeping it in place. So you have an actin strand with it, and the actin experiences a myosin pull. So at that point, it sort of moves away from the trap. But then the trap is there to bring it back in position, right? So Brownian motion में थोड़ा सा हिल रहा है. जैसे वो actin का pull आता है, it moves out and then it tries to come back to its position. So this moving out and coming back to position is what is shown here. So every time you see that pull, you see the displacement. You see the displacements, right? So you see intermittent displacements यहाँ, यहाँ, यहाँ. So आपको जब ये दिखता है, then you can now understand कि यहाँ पे अगर y-axis में distance plotted है, then what is the average distance that this bead has traveled? That would give you an idea of the force that this one single heavy meromyosin is putting on the actin. So if you look at the profile of the distances that this bead has traveled, you would see that the median or the mean distance turns out to be around 11 nanometers. So around 11 nanometers is the displacement of this bead every time the heavy meromyosin pulls on the actin. So that is the amount of displacement that occurs when the heavy meromyosin binds, exerts the power stroke, and moves or slides the actin. If that is the case, if that is the case, what is the force acting? The force, if you calculate now, turns out to be of the orders of piconewtons and turns out to be somewhere around, say, 3 piconewtons. There are some caveats to this. One is that everything, this whole actin cycle is dependent on ATP hydrolysis, right? So it all depends on ATP. Agar ATP bound hai, ATP hydrolyzed hai, then ADP is released, ATP binds back. So everything depends on ATP hydrolysis. So what would happen if you decrease the amount of ATP or you increase the amount of ATP? So this is exactly what they did. They did this entire experiment at 2 millimolar ATP or 10 micromolar ATP. What they found was that if you change drastically the amounts of ATP, lower it too much or increase it to the maximum amount possible, you do not see a change in the distance that is traveled. The distances still keep the same, about say 11 nanometers. What we showed here is the Gaussian profile, but you could have something going as close to say 15 nanometers, 18 nanometers, on an average 11 nanometers. So that profile still remains the same, whether you go for 2 millimolars or 10 micromolars, right? Which means that this brings us back to the question that one of you had asked in the last class कि एक ATP hydrolysis से क्या एक step होता है? So this whole game comes back to that. So if you think now that one ATP hydrolysis is giving rise to one step, then it would definitely give rise to, अगर आप ATP concentration बढ़ाते भी है, तो वो step के numbers बढ़ जाएंगे, but step size नहीं बढ़ सकता. वो step size आपका same ही रहता है. So the step size here and the distance that of the slide or the sliding of the actin, the amount of sliding of the actin still remains the same, and you can see that very clearly from this profile, right? Okay, एक और चीज है. Suppose I'm able to, so this is the last thing for today. The caveats are here, but this is the last thing I'll explain for today. Suppose instead of having say 4 say low amounts of meromyosin on a bead, you have a bead जिसपे आपके meromyosins के numbers थोड़े बढ़ गए हैं, because you're not able to control these cross-linking reactions. These are reactions you cannot really control. So you can make them low, but you cannot negate the chance that one of the bead has been, say, instead of 4 meromyosins attached to it, has 14. हो सकता है. अगर ऐसा है, or if you artificially increase the meromyosin content and you have more meromyosins now attached to a bead, then what's the scenario? The scenario is this, that you would have multiple meromyosins then acting on an actin filament, right? Now if you have multiple meromyosins एक साथ actin filament को slide कर रहे हैं, तो आपका ये जो distance traversed by this bead है वो बढ़ जाएगा, because you have too many of these meromyosins sliding it. So एक साथ 10 nanometer का sliding, लेकिन ये भी एक और 10 nanometer, so it becomes a cumulative effect, right? That is what you see here. If you have high meromyosin, तो वहां पे क्या होता है, आपके वो step sizes जो है वो same है, लेकिन बहुत सारे steps बन रहे हैं. And so you see what is called a cooperative nature of these meiosis, that they cooperate together to create a much larger displacement and a larger force. तो यहाँ तक ही हम आज देख रहे हैं. So what we have tried to understand in very just a nutshell is how you can trap a bead in this laser profile, how it is kept in position because of two different kind of forces, or not forces, or two different phenomena that's occurring here. One is the phenomena where there is scattering, and there is you have a Gaussian profile and you have scattering of light that is falling on this bead, and that is creating a change on momentum. But because you have this Gaussian profile, तो ये जब भी यहाँ जाएगा, तो because of balance of forces, it's always brought back. Another thing that we have seen is that this itself has a dielectric. So this gets caught up in this electromagnetic radiation, much like a flag gets caught in wind. So जैसे अगर आप flag को रखते हैं and there is wind, you would see the flag moving. So it's more like that. This dielectric gets caught in this electromagnetic radiation. And in the end, any displacement of this bead can be measured, and you can directly from that estimate the force that is acting on it. And this can be translated to, if you translate this knowledge into this system where you have actin which is bound to the two beads, and you have myosin actin on the actin which is pulling. So you have a restoring force of the bead, but the bead is in Brownian motion. हमेशा आपको ऐसे दिखेगा कि it's a little wobbly. It's in the center, but it's always wobbling. So you'll always see these small lines coming up. But every time the actin is pulled, you would see the bead moves, but the bead is restored back because of restoring forces. So it comes back, and you can see those spikes in the distance moved by the bead, and those are always near about, say, mean of 11 nanometers, whether you do it at low ATP concentration, whether you do it at high ATP concentration, showing that there is a step movement of myosins. Okay, so far, do you have any questions?
Ma'am,
Yes, Sarika.
when the concentration of ATP increases, so then the cooperative effect is there or not? Means if the cooperative effect is produced when there are more myosin head. So in the case of ATP, increased concentration of ATP, the size of the step does not increase.
अच्छा, size of the step कैसे increase होता है, आप बताइए मुझे.
You said na that when there is cooperative effect, if it's moving 11 nanometer in cooperative effect, there would be a long displacement.
हाँ, so let me simplify this. You have this bead attached to actin, and I'm saying that every time the one myosin head binds to it and it pulls it, है ना, तो you see one displacement. तो एक ऐसे sharp up and down, that is what you've seen, right? Up and down, you see one displacement, and then restoring force, it brings it back. अभी आप ये सोचिए कि एक myosin head ने ऐसे मूव किया, दूसरे मायोसिन हेड ने मूव किया, वो और थोड़ा मूव हुआ, तीसरे मायोसिन हेड ने मूव किया, वो और थोड़ा मूव हुआ, चौथे ने मूव किया और थोड़ा मूव हुआ, then all of them fall down, it goes back because there is a restoring force. So in that case, what do you see? You see step size is same hai, but you will see one jump, you see another jump, you see another jump, until you would see that all of them would lose the bound ADP, will be bound by ATP, पूरा वो actin से वो dissociate हो जाएगा, then you will see a sharp down. You understand this? But बहुत simply सोचो, bead है, actin है, मायोसिन ने उसको होल्ड करके रखा है, मायोसिन ऐसे मूव कर रहा है, आपका बीड मूव कर रहा है ना, मायोसिन डिटैच हो गया है, बीड कुछ है नहीं जो उसको ऐसे पकड़ के रखे, एंड देन देयर आर रिस्टोरिंग फोर्सेस, इट गोज बैक. सो यू सी द शार्प अप एंड डाउन. यहाँ पे मैं क्या कर रही हूँ, मैंने बहुत सारे मायोसिन हेड्स एक साथ लगा के रखा है. बीड को छोड़ दीजिए, आप सोचिए कि किसी तरह एक्टिन के ऊपर हमने बहुत सारे मायोसिन हेड्स डाल दिए. अभी एक ने मूव किया, you see a movement of the beat, दूसरे ने move किया another beat, तीसरे ने. So what you see is not one movement up and the down, but you see up and then up and then up. तो यही हमें यहाँ दिख रहा है. Oh, I've stopped the slideshow, have I? एक स्टेप, दूसरा स्टेप, तीसरा स्टेप, स्टेप साइजेस नहीं बढ़ रहे हैं यहाँ पे. जो हो रहा है कोऑपरेटिव नेचर की वजह से आपके मल्टीपल स्टेप्स इंटीग्रेट हो गए हैं. Until you see that all these ADPs have been converted, have been exchanged for ATP, and the myosin heads sort of detach from actin, and you see the restoring force is then going to push this bead back to the center.
Okay, ma'am.
Any other question? Okay. If not, then we will stop here today. Optical trap is something that we will refer to in a number of classes, because this is essentially, as you can understand, it's something that gives you a beautiful way to measure things in this nanometer scale. वरना कैसे measure होगा? तो this has been used for almost all biological motors. Any biological motor you think of, you know that an optical trap has been used. So this was an introduction to optical trap, and we are going to refer to optical trap experiments in the coming days too. So just remember this part कि optical trap का basic concept क्या है, बस इतना ही काफी है आप लोगों के लिए. All right, thank you so much, and we'll meet again tomorrow at 8 a.m. Thank you.
Thank you, ma'am.
Thank you, ma'am.
Thank you.
Thank you, ma'am.